Hey, up next, it is my pleasure to introduce new KIPAC postdoctoral fellow, Zhefu Yu, who is going to tell us today about mapping the accretion onto supermassive black holes in the time domain. Take it away, Zhefu.
About what KIPAC content super research for understanding the accretion disk around the supermassive black hole. So supermassive black holes only exist as the centers of massive galaxies, and how supermassive black holes form and grow over cosmic time is one of the key questions in the current emphasis. And when the supermassive black hole is actively growing to accreting the surrounding gas, the energy output from the galactic nuclei can have a significant effect on the star formation in their host galaxy. So understanding the growth of supermassive black holes is also a critical part for understanding the evolution of galaxies over cosmic time. And in order to understand the growth of black holes, there are at least two goals we must achieve. First, we need to accurately measure the mass of the black hole. And secondly, we need to have a clear understanding of the accretion disk around the black hole, because accretion is the major part of the supermassive black hole growth. And in this talk, I will focus on the accretion disk, but if you are also interested in the black hole mass measurement, I will be happy to chat afterwards. So the accretion disk in the active galactic nuclei is generally too small to be safely resolved. So one of the major methods to study the accretion disk is through the time domain. The continuum emission from the accretion disk has generally a strong time variability.
So conventionally, this variability is explained by a lamppost model, where the variability is driven by the fluctuation of a compact central lamppost, as is illustrated in this cartoon. And this fluctuation from the center then propagates outward at the speed of light to drive the fluctuation at larger radii. According to this lamppost model, there will be a time delay between the variation at different wavelengths of the continuum due to the large travel time from the hot inner disk to the cold outer disk. And therefore, by measuring this continuum time lag, we can get the size of the accretion disk, which is a critical parameter for constraining the accretion disk models. And in one of my previous papers, I measure the accretion disk sizes using the photometry from the standard star fields of the dark energy survey. The left figure here shows the distribution of the observational cadence within these fields. Here we can see that most of these fields we used have nearly daily observational cadence, which is very high compared to similar studies within the field in past works. And in this paper, I measure the accretion disk sizes for 22 quasars. And in the right figure here, I show our measurements in the accretion disk size versus black hole mass plot. Here, the data point shows our measurements, while the three lines here shows the prediction of a standard geometrically thin optically thick accretion disk model with different Eddington ratios. Here we can see that most of our measurements are in general agreement with the prediction of the standard thin disk model. This is in fact a very interesting result because it is in contrast to some local agents where people find a much larger accretion disk sizes than the model predictions. And in the future, I plan to get involved in the Rubin SST survey and use the photometry from the deep drilling fields to measure the accretion disk sizes using continuous reverberation mapping. Taking advantage of both the deep and high cadence observations in the deep drilling fields, I expect to increase the number of accretion disk size measurements by more than an order of magnitude compared to the current sample we have. Moreover, the decade-long observations from SST would also allow me to directly test the reliability of the lamppost model over a long time scale. And on the other hand, I also plan to work with the XOC group in KIPAC to study the innermost region of the accretion disk through the X-ray reverberation mapping. This region is particularly interesting because it allows us to study the behavior of materials under a strong gravitational field where the effect of general relativity plays an important role. Okay, I will leave my summary here. Thanks for your attention, and I will take questions.
Thank you, Zhefu. Hey, and we've got time for a few questions. Yes, Yao.
Thanks for the talk. So since you are already able to measure disk size with DS, I'm curious, do you need a deep drilling field from Rubin to do this? Or is the wide field that can give you more sample for your science?
Yeah, that's a good question. So what Rubin can provide us, especially the deep drilling fields, firstly, it has much deeper observations compared to what we have. For example, compared to ZTF or some previous observations with DS or other surface as well. And on the other hand, the observational cadence is also extremely high. So basically, the baseline cadence in the deep drilling field is about 3 days, but some white papers also proposing a 2-day cadence within this field. And combining these two, so through some previous simulations, I expect that we can get more than an order of magnitude more disk sizes than what we have. And this significant increase in the sample size would be a significant difference in this field. And also at the same time, this higher quality data would also allow us to get more accurate measurements of the disk size compared to what we have previously.
And a question from Andrew.
Thanks for the talk. I'm curious about what sorts of AGN you have in your population. Are they all just standard quasars, or do you have like radio galaxies in here as well?
Yeah, basically, for my study with the accretion disk size, most of them are just standard quasars and spanning relatively a wide redshift range.
I guess that kind of a related question I had to that. So you said that in the sample you had, there didn't seem to be this problem that's been popping up all over in AGN accretion disk studies, that in a lot of cases, the accretion disks seem to be too big compared to the standard model predictions. But you say that your sample isn't showing that. Is there something different between this sample and the sample that do have the accretion disks looking like they're too big?
Yeah, this is a very good question. So I think the answer to this question has two aspects. The first aspect, as you mentioned, is mainly in a difference of the sample. So for this sample we are sampling a variety of redshifts from local to, I think, as high as a redshift of 2-ish. While for the study that find the larger disk size, they are mostly local AGNs. In that case, it is possible that the local AGN only represents a subsample of the whole AGN population. However, on the other hand, this problem may also relate to how you use the thin disk model to predict the accretion disk size you should have. So basically, what the model predicts here is weighted mean of the accretion disk. And in that case, it's a problem of how you weight the light you get. Basically, if you weight them by flux or weight them by responsibility, it's kind of a different prediction. So what we find is that if you use a different weighting in your model prediction, then most of our disk size measurements would be higher than the prediction of the thin disk model.
Okay, interesting. So it sounds like it's somewhere between the model interpretation and the sample.
Yeah.
Okay, well, let's thank Zhefu again.